Hazard, a learning-based, large-scale discovery of hidden sensitive operations in Android applications. Take it away.
Thanks. Good morning. I'm Xiaorui Pan from Indiana University, and the topic of my presentation is learning-based large-scale discovery of hidden sensitive operations in Android applications. In last decade, automated runtime analysis system has been widely deployed in security industry, and overall it has been effective against malware in both Android and desktop platforms. However, security is never one-size game, and the malware authors have come out countermeasures against this automated runtime analysis system. We call these countermeasures as hidden sensitive operations, which means malware or benign applications will conduct the sensitive operations only on certain conditions to hide from automated runtime analysis. And this is a code snippet from Hacking Team remote control system. Hacking Team is a professional spyware provider for government agencies across the world. And in the summer of 2015, Hacking Team was hacked, and their software has been posted online. And in this code snippet, we can find that the Hacking Team application will try to determine whether they are running in an emulator. If so, they will simply return. If not, they will try to root the user's phone and also begin to monitor user behaviors and send back this information to the server. Since hidden sensitive operations could include anti-emulator behaviors, just as we find in Hacking Team code, but it could also include anti-sandbox behavior. And it has been reported that FireEye sandbox has been profiled once, and the malware will simply stop their malicious behaviors once they find the presence of FireEye sandbox. And it could also include logic bombs, which could be based on time and location. And in the recent development, we can find that the runtime analysis technique has become even more advanced, and the malware could determine the presence or absence of a real human user to differentiate from automated runtime analysis without a human user. So how to solve this problem? And there are some existing work in both academia and industry, and the Morpheus has tried to extract all the possible heuristics that can differentiate an emulator and real Android devices. However, the system cannot be solved as a detection tool directly, otherwise it will cause very high false positive. Trickerscope uses semantic execution to detect logic bombs in Android applications. Due to the nature of semantic execution, it's very heavy. Therefore, it has some performance issues. And also, they needed to do some customization for certain types of triggers. And so therefore, it makes them need to know the types of triggers in advance. So currently, the limitation is that they are only limited to time, location, and SMS-based logic bombs. And in the industry side, to the best of our knowledge, currently, industry try to address this problem by manual analysis, by case analysis, and they will generate the signature. Our approach is quite different from existing works. We use lightweight program analysis techniques to extract features, and these features are based on unique observations. Each of these features themselves might not be powerful enough to detect HSO in a precise way, but by combining all these features together and using machine learning, we find that it's feasible to detect HSO with a satisfying precision and also recall. Because our features are extracted from lightweight program analysis, so it has achieved scalability. And indeed, the scale of our study, which is conducted upon 300,000 applications, is larger than any other previous study. And also because these features are defined not based on certain types of triggers or certain types of sensitive operations. So our system is also a first step towards a more general approach. We have three key observations. The first operation is that the data and the semantic dependency between conditions and passes in HSO are usually weaker than normal cases. Let's also take hacking team code as an example. We can find that the variables that has been used in the conditions, which is whether this is emulator or not, has never been used in the both passes after that. And this is quite different in normal conditions. In normal cases, we find that, for example, this application uses location to register service. And we find that the variables has been used in the passes has a direct data dependency upon the variables in the conditions. And in other cases, there might be not a direct data dependency upon the variables in conditions, but there usually are some semantic relevance, such as in conditions, they will check whether the Wi-Fi is enabled, and then they will do Wi-Fi connection in the passes. We consider the differences between HSO and non-HSO in this observation is fundamental. Because the check in HSO is only serves as a guard of malicious behaviors. Once the environment is assured to be secure, then these variables are likely not to be used again. The second observation is that the behavior differences between two passes in HSO is significant. Also in hacking team code, the one pass, there is no sensitive behaviors at all. And the other pass, they will try to do root explore and to monitor the user behaviors. Essentially, in HSO, one pass is just serve as a decoy for another pass. And the other pass is actually will do the real job, which means sensitive operations in this context. And the third observation is that the sources of trigger conditions in HSO is usually coming from system properties. Because in HSO, the conditions want to check the environment to make sure they are safe to conduct their sensitive operations. So they usually will check the system properties. It's also true that non-HSO will also check system properties. But statistically, according to our study, the majority of non-HSO will check the local variables. So based on these three observations, we have come out our implementation, and this is the architecture of our implementation. It contains three parts. We first did a control flow analysis and backward data flow analysis as a preprocessor. Then we extract features based on trigger analysis, path behavior analysis, and also trigger behavior relation analysis. Then we train a SLM classifier based on a small neighbor dataset. Then we do 2 rounds of retraining to boost the diversity of both HSO and non-HSO samples. And here is the details of our features. And the overall have 3 categories of features. And each category of features is related to one observation we just introduced. The first category of features is the data and the semantic dependency between conditions and passes. And we calculate the data dependency as a percentage of variables in passes that are related to variables in conditions. And also, we have measured the semantic relevance based on whether there is an implicit relation. And this is a table of examples of key and API pairs we consider that has implicit relations. And this table is generated based on semantic relevance and also frequency analysis. And the second category of features is based on the behavior difference between the two passes. And we have 2 distances in this category. The first category is the data distance. The data distance is defined in this formula. And the intuition is that the more shared variables, more shared fields of reference classes between 2 passes, the shorter the data distance between these 2 passes. And the second distance is the activity distance. We group APIs or system keys based on the functionalities, and then we calculate the JCAT distance between the 2 passes. And the third category of features is the source of trigger conditions. As we said in the observation part, we care about whether the variables in the condition is coming from system properties. And the list of system properties has coming from SUSE, which is a previous work. We have two separate data sets. One is for ground truth, one is for our measurement study. And in the ground truth, we have 213 neighbored positive data set and the 213 negative data set. And in the large scale data set, we have more than 120,000 Google Play applications and more than 200,000 voice tutor applications. And this is the evaluation result we conducted based on the two separate data sets. And in the ground truth data set, we did a cross-validation and find that both the precision and recall are satisfying. And in the large data set, due to the scale of the data set, we can't do a full data set evaluation. So we use the random sampling to verify the precision. We find that the precision is around 98%. However, we are not 100% sure that there aren't any unknown HSO in the wild. So for this data set, we don't have the recall. And this is the performance of our system. And to measure the performance, we randomly sampled 3,000 applications from Google Play. And the average size of these applications is around 8 megabytes. And averagely, it will cost about 760 seconds for one app. And we also compare the performance of our system with TrickScope. And upon their data set, our system is about 5 times faster. And in this part, we introduce the measurement result. Overall, there are about more than 18% of applications in the wild that will contain HSO. But the majority of these HSO actually are related to shared libraries. So in terms of unique HSO instance, we have found about 3,500. The graph shows a distribution of HSO upon countries. If we compare the percentage of HSO applications with the cost per install, we find that Russia really stands out. This graph shows the relation between HSO and PHA, which means potentially harmful applications. And we find that there indeed is a positive correlation between HSO and PHA. And this graph shows the distribution of triggers. We found that although, as expected, that the majority of the triggers come from device information and system event and also time and location, but do find some HSO actually are based on user interface. We will talk about more about this in the case study parts. And this graph shows the general trend of HSO in the wild. We find that there is an increasing trend of using HSO. So we think this raises the urgency of come out more efficient countermeasures. And this is one interesting case. It's, this application uses video to guard their sensitive operations. Most automatic runtime analysis system will use automatic click to explore the interface, and such as monkey click. And because these clickers usually don't wait the video to be fully loaded, so if application try to guard their sensitive operation like this, so the monkey clicker will likely to fail. And also, in this case, the sensitive operations are guarded by a condition, which is the time interval between two clickers must be larger or equals to 0.5 seconds. This is also because automatic clicker, such as monkey clicker, you usually try to click as more as possible within a very short time window. Here is the conclusions of our study, which is First of all, we find that it's very promising to combine machine learning and night-weight program analysis. Although the features generated by night-weight program analysis might not be very powerful in terms of individual feature, but we find that it's very promising to combine machine learning, then make the use of the differentiation power of all the features together. And if we do that, we can achieve both scalability and also accuracy. And second, that our study is the first step towards the generic innovation detection technicals. We verified the feasibility of such kind of technical in our study. And also by going through more than 300,000 applications, we confirmed the prevalence of HSO in the wild. And this raises the urgency of coming out with more efficient countermeasures. And that's all for our study. And any questions will be appreciated.
Thank you very